Hi, welcome to question 5. So a little review before we get started. Remember that for a binary min heap, the min heap property is that every node below the parent has to be greater than the parent. In other words, as you go up the min heap, the values of these nodes are going to decrease because you want the minimum element as the root. And so if we look at an implementation of a binary min heap as an array, the smallest element is going to be towards the front of the array, specifically at index 1. All right, so traditionally we try to start the elements, fill them in from index 1 of our array instead of at index 0, just to make the rules easier. And what are the rules? The rule is that if you have a parent node at index n, then its left child is going to be at index 2n, and its right child is going to be at index 2n plus 1. So let's apply this rule. Okay, so I start at index 1, and whatever is at index 1 is always going to be my root. And notice that it's also the smallest element in our array. So 2 is going to be my root. And then from 2, I can see what its children are, because 2 is at n equals 1 index. And so its left child is going to be at 2 times 1, which is 2. So this is going to be its left child. And its right child is going to be at 2n plus 1, which is 2 times 1 plus 1, which is 3. And so this is going to be its right child. Okay, so I have 3 here, and I have 4 here. Okay, so now I move along in my array. Okay, now so originally I was at 2, I got all of its children, and now I'm moving along to 3. So at 3, what are its children? Well, here n is equal to 2. So its left child is going to be at 2 times 2, which is 4. So here is its left child. And then its right child is going to be at 2 times 2 plus 1, which is here. And so the left child of 3 is going to be 8. The right child of 3 is going to be 5. All right, so now I move my pointer along. And this pointer is really just for me to keep track of where I am in my array. You don't have to have this. So for n equals 3, its children are going to be at 2 times 3, which is 6, and 2 times 3 plus 1, which is 7. So 4 is going to have a left child here and a right child here. Okay, and so that means that this is our final min heap. Okay, and the reason I don't have to move the pointers along the rest of the elements in our array is because I know that we've basically covered all of these elements when we looked at their parents. Okay, so now question B is kind of the opposite. So we want to translate this binary min heap, but a little bit different version, back into an array. So what are we going to do first, the binary heap? We're going to remove the min, remove the root, okay? And so what happens in the removal process, let me just copy this min heap. So remember that when we remove min, in our case, the min is always going to be the root node, we first switch the elements in the root and in the rightmost, bottommost leaf node, okay, which in our case is going to be 11. And so we switch those elements. So we have 11 here and 2 here. Let me actually put them in different colors from the rest of the nodes, okay? And now, since we're removing a node, and since we are removing the root node, we don't really care about this node anymore, right? Because it has the value of the root, which we want to remove. And so it makes sense to just remove this node entirely. Okay, so now we have one less node in our binary min heap, but the problem is we have to make sure that it satisfies the min heap property of the parent being the smallest of all of its children, okay? So right now, 11 is not the smallest of all of its children, right? In fact, it's the greatest of all of its children, so we need to make sure that it's put in the proper place. How do we do that? We need to bubble down. So what the bubbling down procedure is as long as the min heap is not satisfied, or as long as 11 doesn't become a leaf node, we're going to look at its children. There might only be one child, but for now, let's say that they're left and right children, and we're going to swap 11 with the smaller of its children. Why do we care about the smaller child? Because we want the smaller values to be up at the top of our binary min heap, right? So we're going to compare 11 with 3 and 4. Okay, 11 is greater than both of its children. If it's not greater than both of its children, then you would need to swap it with the child that it is greater than. Okay, but since it's greater than both of its children, we need to swap it with the smaller child, which in this case is going to be 3. And so we have 3 here and 11 here. Okay, now we check. Is the min heap property satisfied, or is 11 now a leaf node, at which point, because it's a leaf node, we can't really bubble it down any further, so we need to stop? Well, no, right? The min heap property is not satisfied, and 11 is not a root node, so, sorry, not a leaf node, and so we need to keep bubbling down. Okay, so now let's compare 11 with its 2 children. It's greater than both of its children, so again, we need to swap it with the smaller of its children, which is going to be 5, and so 5 is now going to be here, and 11 is now going to be down there. Now we check the conditions again. Is the min heap property satisfied? Yes, okay? And also 11 is the leaf node, which inevitably means that the min heap property is satisfied. And so this is going to be our final binary min heap.